every type of solar eclipse and occultation. Space is complicated. We make it simple. A shadow isn't nothing. It's proof that two objects, sometimes millions of kilometers apart, briefly lined up in exactly the right way. An eclipse is really just geometry, one body passing in front of another from your point of view, but the specific type of alignment changes everything about what you see, how long it lasts, and how rare it actually is. We're going in order of how total the blackout gets, from barely noticeable to reality bending, then we'll sort them a second way, by scale. Because some of these happen every few months and some have happened exactly once in recorded human history. Partial solar eclipses. We begin with the most common kind, and also the most disappointing if you don't know what you're looking at. A partial eclipse happens when the moon passes in front of the sun but doesn't fully align. From your specific location on Earth, you only see a bite taken out of the sun's disk, sometimes a sliver, sometimes most of it, but never total darkness. Here's the thing most people don't realize. Nearly everyone who has ever seen a total solar eclipse was standing inside a much larger region where people around them were only seeing a partial one. The moon's shadow during an eclipse has two parts: a narrow, dark inner shadow called the umbra, and a much wider, lighter outer shadow called the penumbra. If you're in the umbra, you get totality. If you're anywhere in the penumbra, which can span thousands of kilometers, you get a partial eclipse instead. And the further you are from the umbra's path, the smaller the bite taken out of the sun looks. During a total eclipse crossing the United States, for example, the path of totality might only be 150 kilometers wide, while the partial eclipse is visible across the entire continent and beyond. Here's the fact that should genuinely bother you. You cannot look directly at a partial eclipse without eye protection at any stage, because even a sliver of an uncovered sun is bright enough to cause permanent retinal damage. The danger of an eclipse isn't the darkness, it's the fact that our natural aversion to bright light gets fooled by the dimmer overall scene. People stare longer than they should, precisely because it feels less blinding. Partial eclipses happen at least twice a year, somewhere on Earth, making them the most frequent type by far, and also the type most people have technically witnessed without ever realizing it. Because from any random point on the planet, a partial eclipse can look, at a glance, like nothing more than mildly overcast weather. Annular solar eclipses. Here's the twist. Sometimes the moon lines up perfectly dead center, directly in front of the sun, and you still don't get darkness. The moon's orbit around Earth isn't a perfect circle. It's an ellipse, meaning its distance from Earth varies over the course of a month, from about 356,000 kilometers at its closest to about 406,000 kilometers at its farthest. When an eclipse happens while the moon is near that farther point, it appears slightly smaller in the sky than the sun does. Even at perfect center alignment, it simply isn't large enough to cover the entire solar disk. The result is a blazing ring of sunlight surrounding a perfectly black circle, an effect commonly called the ring of fire. It can last much longer than a total eclipse, up to 12 minutes and 30 seconds, compared to a maximum of around 7.5 minutes for totality, because the geometry that produces it is more forgiving, and the path can trace a longer arc. Here's the fact that changes everything about how you should think of these. An annular eclipse never produces true darkness, no matter how perfectly it's aligned. Even at maximum eclipse, enough direct sunlight is still leaking around the edges that you can never remove your eye protection. Not even for a second. Birds don't go quiet, the temperature barely drops, and the sky stays a strange, deep twilight blue rather than true night. It looks otherworldly, and yet it never crosses the threshold into the total experience. And it hints at something deeper. The moon's orbit is slowly, measurably drifting farther from Earth by about 3.8 centimeters a year. The result of tidal forces is transferring Earth's rotational energy outward. Annular eclipses are becoming more common over cosmic time, and total eclipses are becoming rarer. Millions of years from now, the moon will have drifted far enough that total solar eclipses stop happening on Earth entirely, permanently replaced by the ring of fire. Total solar eclipses. Here's the reframe. This is the one everyone travels for. and it earns the trip because it isn't just a bigger partial eclipse. It's a different category of experience entirely. During totality, the moon fully covers the sun's blinding disk, and for a few brief minutes, you can look directly at it with the naked eye, because what you're seeing isn't the sun's surface anymore. It's the corona, the sun's outer atmosphere, a wispy silvery white halo that is normally a million times too faint to see against the glare of the surface below it. Totality only happens because of one of the most absurd coincidences in the solar system. The sun is about 400 times wider than the moon, and also, by almost the same factor, about 400 times farther away. That ratio means the two objects appear almost exactly the same size in Earth's sky, a coincidence with no physical reason behind it, unique among every planet moon combination we've found anywhere in the solar system. Nowhere else that we know of would this specific alignment even be possible. Here's the part that should genuinely unsettle you. Temperature can drop noticeably within minutes, wind patterns can shift, and animals, birds, insects, even farm livestock regularly react as though night has fallen, going quiet, or heading to shelter, all triggered by an event lasting only a few minutes in the middle of the day. Along the horizon, in every direction, you can often see a 360-degree sunset glow because sunlight is still hitting the atmosphere just outside the narrow band of totality you're standing in. And here's the fact that should stay with you afterward. This specific spectacle has an expiration date. As the moon continues drifting away from Earth, total eclipses will eventually stop happening altogether, meaning every human being who has ever witnessed or will witness totality lived during a narrow cosmic window, geologically speaking, that most of Earth's future will never get to see again. Hybrid solar eclipses. Here's the fact that most people never learn. Total and annular aren't actually two separate fixed categories. They're two ends of a spectrum, and every so often, an eclipse falls exactly on the dividing line between them. Because Earth's surface is curved, the exact distance between an observer and the moon changes slightly depending on where on the planet they're standing during the event. In a hybrid eclipse, the geometry is balanced so precisely that the eclipse appears annular, a ring of fire, for observers near the beginning and end of its path, while observers standing in the middle of that same path, slightly closer to the moon due to Earth's curvature, experience a brief total eclipse instead. The same celestial event, crossing the same narrow path on the same day, changes category depending on exactly where you're standing to watch it. Here's the fact that should genuinely bother you. Hybrid eclipses are the rarest of the three, accounting for only about 5% of all solar eclipses, and the total phase within a hybrid event is often shockingly brief, sometimes lasting only a handful of seconds, compared to several minutes in a standard total eclipse, because the alignment sits right on the mathematical knife's edge that makes totality possible at all. Move your observing point a few kilometers in either direction along the path, and the entire character of what you witness changes. But eclipses aren't the only kind of celestial hide and seek. Something rarer, and arguably stranger, happens when a planet blocks a star. Lunar eclipses. Here's a category that flips the entire geometry discussed so far. Instead of the moon blocking the sun, the Earth gets in between and blocks sunlight from reaching the moon. During a total lunar eclipse, the moon doesn't vanish into blackness. It turns a deep glowing red, an effect commonly called a blood moon. That color exists for the same reason sunsets are red. As sunlight grazes through Earth's atmosphere on its way toward the moon, the atmosphere scatters away the shorter blue wavelengths and bends the longer red wavelengths around the planet's curve, projecting a ring of filtered, reddened sunlight onto the moon's surface, even while the moon sits entirely within Earth's shadow. Here's the fact that changes everything about how these compare to solar eclipses. Because Earth's shadow is so much larger than the moon itself, a total lunar eclipse is visible from the entire night side of the planet at once, lasting up to an hour and 40 minutes for totality alone, dramatically longer and dramatically more accessible than the narrow few-minute path of a total solar eclipse. You don't need to travel anywhere to see one. You just need it to be nighttime, where you happen to be standing. Here's the part that lingers. The exact shade of red varies noticeably from eclipse to eclipse, and astronomers use it as an informal gauge of the state of Earth's upper atmosphere. A darker, more brownish red eclipse often follows a major volcanic eruption when extra ash and aerosols high in the atmosphere block and redden more of the passing sunlight than usual. In a real sense, the color of the moon during a lunar eclipse is a secondhand snapshot of conditions in Earth's own sky, reflected 250,000 kilometers away, and bounced back for anyone to see. Stellar occultations. Here's the pivot. This is where the category stops being about the sun and the moon entirely and expands to cover every object in the sky capable of blocking every other object behind it. A stellar occultation happens when any solar system body, a planet, an asteroid, a moon, even a distant Kuiper Belt object, passes directly in front of a background star from Earth's point of view, and the star simply vanishes, sometimes for a fraction of a second, sometimes for minutes, depending on the size and speed of what's blocking it. This isn't a rare curiosity. It's one of the most powerful tools astronomers have for measuring objects too small or too far away to image directly. When an object occults a star, the exact duration and timing of the star's disappearance, measured from multiple locations on Earth simultaneously, can reveal the object's precise size, shape, and even whether it has an atmosphere, rings, or a moon of its own, all without ever needing a spacecraft to visit. This is exactly how Uranus's rings were discovered in 1977. Astronomers were watching a star occultation to measure Uranus's atmosphere, and the star blinked unexpectedly before the planet itself arrived, revealing rings nobody knew were there. Pluto's thin atmosphere was mapped the same way, decades before New Horizons ever flew past it, just by timing exactly how gradually, rather than instantly, a background star faded and reappeared as Pluto's hazy air blurred the edges of the event. Here's the fact that should genuinely bother you. Some of the objects we've measured this way are so small and distant that a direct occultation only lasts a second or two, observed from a shadow path only a few kilometers wide crossing Earth, meaning astronomers sometimes deploy dozens of small telescopes across an entire region on a single night for a 1 in 1,000 chance that any individual instrument happens to be standing in exactly the right spot when the shadow sweeps through. Planetary transits. Here's the fact that reframes the whole category one more time. An eclipse is really just a occultation where the objects happen to be extremely close together, and a transit is what you get when the blocking object is small and far. When Mercury or Venus passes directly between Earth and the Sun, they don't cover it at all. From Earth, they appear as a tiny, sharp black dot, slowly crawling across the Sun's enormous disk, visible only with proper solar filtering equipment, nothing like the total blackout of an eclipse. Venus transits are startlingly rare. They occur in pairs 8 years apart and then don't happen again for over a century. The most recent pair was in 2004 and 2012, and the next won't occur until 2117, meaning most humans who have ever lived have never had the chance to see one at all. Mercury transits are more frequent, happening roughly a dozen times per century, but they're small and subtle enough that most people never notice or bother to look. Here's the fact that changes everything about how astronomers use this category. This exact geometry, a small object dimming a star's light by a tiny measurable amount as it passes in front, is the primary method used to detect planets orbiting other stars entirely. Every time a distant world crosses in front of its own sun from our point of view, the star's light dips by a fraction of a percent, and we can measure that dip from light years away. The same basic mechanism that lets you watch Mercury crawl across our sun with a solar filter is quietly responsible for the discovery of thousands of planets orbiting stars we will never visit. Eclipses on other worlds. Here's the last reframe. Nothing about this phenomenon is unique to Earth. Every moon and planet with a companion object close enough to block a light source produces its own version of an eclipse, and some of them are stranger than anything visible from the ground here. Mars has two small, irregularly shaped moons, Phobos and Deimos, and neither is large enough to fully cover the sun from the Martian surface. Every solar eclipse on Mars is technically a transit or a rapid partial eclipse, with Phobos crossing the Martian sky so quickly, once every few hours because it orbits so close to the planet, that an eclipse there lasts only about 30 seconds rather than several minutes. NASA's rovers have directly photographed these events from the ground, capturing a small, dark, potato shaped silhouette scudding across the Martian sun. At Jupiter, the four large Galilean moons regularly pass in front of each other and cast shadows directly onto Jupiter's cloud tops, visible from Earth based telescopes as small, crisp black dots crawling across the planet's face. A Jovian moon casting a solar eclipse onto its own home planet, sometimes with two moons and two shadows crossing simultaneously in a rare double transit. And on Saturn's moon Titan, thick orange haze in the atmosphere means the sun would never appear as a sharp disk at all during any alignment. Any eclipse like event there would look less like a sudden blackout and more like a slow, diffuse dimming filtered through a permanent smog. Here's the fact that puts Earth's situation back into perspective. Of every planet moon pairing we've surveyed so far, Earth and the moon remain the only known combination where the geometry lines up closely enough to produce a true, sharp edged total eclipse, corona and all. Every other world we've examined gets a transit, a partial dimming, or nothing resembling the spectacle at all. Let's sort these seven again a different way, not by how total the darkness gets, but by scale. On the local end, solar eclipses, visible only from a narrow path on one planet, lasting minutes at most, an event that requires you to be in a specific place on a specific day. On the galactic end, exoplanet transits, the same basic geometry used to discover entire worlds orbiting stars trillions of kilometers away, detected not with the naked eye, but with light sensitive instruments capable of measuring a dip of a fraction of 1%. On the frequent end, partial eclipses happening multiple times a year somewhere on the planet, and stellar occultations happening constantly every night for objects too small to notice without deliberately watching for them. On the rare end, total solar eclipses at any single location, which on average return to the exact same spot on Earth roughly once every 375 years, meaning most places on the planet will go centuries between total eclipses passing directly overhead. And on the vanishing end, total eclipses themselves, cosmically temporary, on their way to becoming annular eclipses permanently as the moon continues its slow retreat. Here's the last thing worth sitting with. Every kind of eclipse or occultation on this list is really the same simple fact, dressed up in different geometry, light travels in straight lines, and every object in the sky occasionally gets in another object's way. That's all an eclipse is. And yet that simple fact has let us map the rings of a planet we've never visited, measure the atmosphere of a dwarf planet we hadn't reached yet, discover thousands of worlds around other stars, and given every human who has stood beneath a total eclipse a memory that some of them describe without irony as the most profound experience of their life. All from the same basic trick of one shadow, briefly, falling in exactly the right place. Not bad for stick figures on a rock.